Hello, fellow astro enthusiasts. Recently, I was on a business trip where I took my Dwarf 3 Smart Telescope with me, and while I was imaging some of the targets from the rooftop of the hotel, I was accompanied by some of my colleagues, and they were watching the stacking process in the application. And after some time, one of the colleagues mentioned that why is the image not improving that much? And I think it's an excellent topic to discuss about. And we should look at some of my examples that I was taking with the Dwarf 3 Smart Telescope and also with my 8-inch Dobsonian. And I would suggest let's go straight into PixInsight. So we are at PixInsight, and we first need to talk about when we are capturing the signal from the DSO target. We are not just capturing the light, but we are also capturing the noise. And the relationship between the signal that we are capturing and the noise is called in astrophotography also SNR, so signal to noise ratio. And in fact, if you want to double the signal of an object within the image, we need to spend not 2 times more, but 4 times more under the stars on the same target. And if you want to triple the signal, we need to spend 9 times more on the target. And if you want to quadruple the signal, we need to spend 16 times more on the same target. So because of this, I have three examples of the Pleiades, the M45, and this is 25-minute stack. This is 100-minute stack. So the difference between those is that in this example we have 4 times more integration time compared to the picture on the left, which is 25 minutes. And then the last one will be 1000. It's called 1000, but it's, I believe, 852-minute image total integration time. So this would bring us between this and this image, this is triple the signal in the 852-minute long exposure compared to 100-minute long exposure. So let's firstly focus on the first image. So as we can see, the Pleiades are visible but are not that detailed. So we immediately see that on the picture with the 100-minute exposure, the amount of details, if we compare the views, is uncomparable. We can see a lot more stars in the star field in the 100 image version compared to 25-minute version. And if we compare it to 1000-minute version, it's the same case. So basically, the difference between this image and this image, so 25 versus 852 minutes, is that we have almost 6 times more signal to noise ratio. So this is about the integration time. By the way, on all of those three images, I have applied just after the stacking the background extraction and blur exterminator. So this is not the stack that would come out from the PixInsight stacking process. So just keep that in mind, but otherwise the pictures were not edited at all. So let's minimize this. And I want to show you the fully processed version. So this is 25 minutes. And as you can see, I was able to extract much more nebulosity compared to the initial stack. So this is fully stretched image, as you can see. And this is still in its linear state. So as you can see, this extracted version is similar to the 100-minute version in terms of the nebulosity that is showing up. But with the 25-minute stack, we have also a lot more gradient, which is this purplish color, compared to the stack of 100 that I will show now, the processed version. So here you can see the purplish gradient is well controlled here in this 100-minute stack, and also more of this gases and nebulosity is visible compared to what we have had initially. So this is basically the same picture but processed. And let's check the fully processed 1000 image. So this is only blur exterminator and background extraction, and SPCC as well. So this is the color correction, and this is the fully processed version of Pleiades. So a lot more gases visible. I mean, to be able to capture such an image with this one, I wouldn't imagine that this would be possible. But this is 852 minutes on the Pleiades with the Dwarf 3 Smart Telescope. And I was able to pull much more details from the data during post-processing, as you can see per the result. So this was Pleiades, and let's move to other targets. So that was Pleiades, and just to show you another example, so I have LDN1235, which is the Dark Shark Nebula, also taken with the Dwarf 3. And this is already post-processed image, which will be the case in most of the example images that I will show here. And I'm shooting this from my home, my Bortle 4 location at 49 degrees north. So this is, as you can see, the head is clearly visible, but the other parts are yet hidden in the background, and I couldn't extract that much details from these images. So let's compare how adding more data will improve the stack. So this is 21 hours of data. I tried to process it a little bit differently to bring out the fainter nebulosity, but it's still not the one that I would expect. And then later on I added 7 hours of data, additional 7 hours, and this is my final image that I was able to post-process of the Dark Shark Nebula from Dwarf 3 Smart Telescope and my Bortle 4 location. This is 28 hours of data, and as we can see, the fainter structures of the surrounding gases are forming the shape of the shark much clearly compared to what we have in the 14 hour of data. And just to do a quick math, if we say that we have had 14 hour of data and this is 28 hour of data, so we divide that, we have exactly double the integration time between those two. Let me hide this 21. So there is double of time spent on this target, but the amount of signal to noise ratio that we are improving, we have to actually do a square root of this number, and we get that we have improved the signal to noise ratio only by the factor of 1.41, or in other words 41%. Around 41% of the signal that contains the 28-hour image compared to the 14-hour image. So at some point you run into the diminishing returns where your image will not be improved that much. So, but I'm pretty satisfied with how this image turned out from such a small telescope that Dwarf 3 is, and yeah, this was the Dark Shark Nebula. Okay, so going further, I have also pictures from the Dobsonian that is behind me, and this is the example from the Leo triplet. So this are galaxies M65, 66 and NGC 3628, if I'm not mistaken by the designation. But this is also called hamburger galaxy. So going into comparison between those two pictures, we have 20-minute exposure and 4 times more, meaning that we are doubling signal to noise ratio in the second image, and we are able to see the differences immediately on the post-process picture. I tried to post-process the picture to the best of my abilities, and yeah, as you can see, what comes straight out from those pictures is that this picture shows more color. You could extract more color from this galaxy compared to the background, and here we can see that it is more blended with the background of the night sky. The same with other galaxies, so I don't know if this one is M65 or M66, doesn't matter, you can correct me in the comments. But as you can see, there are a little bit more details that I could see, and the colors are again more washed out with the background compared to what you can clearly separate the dustier regions from the background, and of course the galaxy itself. And again, this one is either M65 or M66. I always mix up those two. But you can see that the dust lanes are more pronounced in the 80-minute version. So yeah, that's an overall comparison. Maybe more details would show up if I would add more integration time, but the issue is that I am imaging this kind of targets with the Dobsonian, and this is causing on the bright stars the Newtonian spikes, and my platform tracks for around 65 minutes. Then I need to relocate the target again and basically start from scratch the second stack. So the second cycle on the platform will cause this. Then as the object moves through the night sky, and you have to recenter the object in the field of view, this is causing that the angle of the object changes. So it's different to equatorial mounts, where the angle of the object, as long as you do not rotate the sensor in the imaging train, does change in with the equatorial platforms. And what I want to show you is also another example where I have shot Horsehead Nebula, and I have 3 examples. So this is 89 times 30 seconds, so around 45 minutes of exposures. This is 263 times 30 second exposure, and this is 410 times 30 second exposure. And these Newtonian spikes, as you can see, I was able to control within 2 platform cycles, but as the object changes, the angle on the night sky, it changes also the diffraction spikes that are caused by the secondary mirror in the Newtonian, which is this one. This is the secondary mirror holder, and this one is causing the spikes. And when the object changes its angle, it also changes the angle of this spider. So this is what's causing those doubled spikes. But as you can see, besides the defects that you can see on those doubled Newtonian spikes, the amount of details that you are able to extract from the image with adding more exposure is mind-blowing, I would say. So this is 89 times 30 seconds, 263 and 410. And by the way, I was showing this picture when I was doing the video about how to do the astrophotography with the Dobsonian, so you can find it on my channel. So if you have found value in this video, please click like and subscribe, and I have already stuff prepared for my channel, so there is new gear already at my disposal. I'm still waiting for my mount to arrive, and I'll be transitioning towards traditional astrophotography setup, and I plan to do a series about it. So stay tuned, and I'll see you next time. Bye bye.